Great pleasure to introduce José here from the University of Miami, who is speaking to us today on higher chordality. Thanks, José.
Okay, thank you very much for the invitation. Great pleasure to be here. And as we said, I'm going to be talking about higher chordality. So chordality is a basic notion for in graph theory, which appears everywhere in various parts of graph theory. And as maybe some of you know, combinatorial topology has been trying to deal with higher with generalizations of chordality, with generalizations of graph properties to simplicial complexes in general. So one of the questions that we asked a few years ago with my two co-authors, Karim was whether you can actually generalize chordality for higher dimensional with the original intent of solving polytopes. Today, let me just wait a second here. So I'll give you a small outline of what I'm going to be talking about. So I'm going to start by recalling what chord graphs are and why do we care about them. Try to put it from or to study them from a topological point of view. I'm going to give Reisner theory. It's very basic, not too much. And the goal of the talk is to try to convince you that chordality of graph is a homological property that you can generalize in higher dimensions. And so the nice properties of graphs do not tend to hold in general. Several of them in granularity, and that provides a lot of interesting examples and computational tools. Future. Let me start by giving you a few. So I'm going to use delta G to denote graphs. I'm going to use delta to denote a simplicial complex of graphs as one-dimensional simplicial complexes, and a V to denote the set of vertices of either graph or simplicial complex. Vertices I'm going to write, so the subscript W is you note induced subgraph or induced subcomplex, and two important kind of graphs that will appear over are the cycle of length n, which is whatever you can the size is, it's the obvious graph, and the complete graph Kn, which is the graph on n vertices where everything is an edge. So chordality. So a graph is a triangle. So what I mean, if I have a cycle of at least 4 below in the picture, then in the graph I can also find at least one edge. For every cycle that I can find which is longer, which length at least 4, I can find one of these chords, and so big points inside the graph have one. So I want to think of this as an abstract object, not necessarily a geometric one. And for let me just take this example here of a hexagon with a triangle in the middle. You can check. Doesn't matter which. So take any pentagon or any quadrilateral. It has at least one diagonal. Question so far. So the definition of a chordal graph.
Rephrase this definition as something about if you take the click complex and you talk about pi1 arrangement.
I'm going there. What I want to do is rephrase all these things in terms of topology in a second.
Awesome. Cool.
Going in that direction, The idea is, so you can already get that since there's cycles there, you can think of them as elements in H1. But you have to fill the holes with big complex. We have this example. So graphs are graphs that are in computation basically because they have these two interesting properties. These are theorems by the 60s. This one says if you chordal graph G, then you can find a vertex V, so that if you have the neighbors of this vertex, the induced subgraph is complete. So right to that graph, you see a complete right next to one of the vertices, you see a complete vertex. And if you take a subgraph, induced subgraph of a graph, it's again chordal. And so you basically graph by removing one vertex at a time, and then what you're putting, so the vertex that you're removing only sees a click at the graph at every step of the removal. For example, in our example, which are dual clicks. So for hexagon, which is very simple, so it's you can check and which are perfect, which ones do see clicks. So you can check, for example, that 2. So the neighbors of are 1 and 3, and if you look at them, they're connected by an edge, so it's complete. Which means that 2 is that I could eliminate. It has a neighbor which is complete. But 1, for example, the vertex is not, because if you neighbors of 1, 6, 5, and 2, the induced subgraph is just the path 6, 5, 3, 2, which is not complete. It misses some edges. The other property of chordal, and why these are very nice, is let's say chordal graph, and you have two vertices which are not neighbors. I want to find the minimal subset of vertices that separate them. And if I have so if my graph is connected and I can walk from U to B, a set of vertices such that every path from U to B crosses at least one of these guys. Or if I get two different components, and the term of Dirac is that if you take any two vertices which are not neighbors and you look at the induced subgraph on any minimal cut, you get a complete graph. The strong minimal cuts and minimal cuts is rather trivial. So and let's try to see let's understand a few cuts here. For example, if I look at the vertices 1, 4, we have split one. You can see that so 1 is connected to 4 to 5 and 3, and 4 is connected to 5 and 3. So you only have to remove those two guys, and that's the only minimal cut. If you want to remove 6, you still have to remove 5 and 3, or if you want to remove 2, you still have to remove 5 and 3, and the induced subgraph on 5 and 3 is an edge. It's present there. And so these minimal cuts are widely used in optimization and understanding the minimal cuts. So for chordal graphs, we understand what minimal cuts are. These are quite interesting properties. Okay, so for logical version of this, and so if you know maybe to refresh or define the following, I'm going to the ring associated to any simplicial complex, the standardized ring. I'm going from graph to simplicial complexes. So if I take a simplicial complex delta on a vertex at B, I can and I fix a field K. I'm going to finally write the ring K delta to be the polynomial ring where there's one variable for each vertex, and I mod out by the ideal, so what is called the Stanley ideal of delta, which is the ideal generated by all products of subsets of the vertex set which are not faces. Okay, so visual as a K as a vector space over K standardized ring is generated by monomials whose levels form faces of the complex. So each monomial in the standardized ring, you get faces of the simplicial complex. That if you have, there's a rich dictionary between algebraic properties of K delta, combinatorial properties of data, and topological properties of the relation of the simplicial. For now, let me do a trick, and this is probably answering or addressing question. I'm going to take the graph discussed earlier, but I'm going to fill all the triangles that I can. So that process is called take the click. I'm going to define it right next to it. But let's imagine that we have this simplicial complex in which the vertices, so triangles, for example, 1, 5, 6 are filled. Okay. And so the thing of this ideal, you can check that the minimal, so the means of the simplicial complexes, the simplicial complex are the 2, 6. Oh, usually wrong. I'm sorry. So 2, 6, 4, 6, and then there's 1, 4, 3, 6, and 5, 2. So there's but it's surrounded by monomials in degree 2. And it's not so I apologize for the mistake. But the following we can think of course in terms of topology and algebra, but for this we need to pass to the click complex. So that if you fix the one skeleton, you add simplices as you can without adding more edges. Or so basically for the complex that you have in you add complex on vertices, and then you want to characterize Cuddle graphs. There's the following very nice characterization. Either that J is Cuddle, so fix any field. Either Cuddle, complexes of this click complex of this field, all the holes are tractable spaces. All these subcomplexes of click complex of G are cyclic over K or over ring if you want to. Homological properties of the standardized ring. You can say the standardized ring has a linear resolution over the polynomial ring, not over K. I will explain what this is, but in some that from quantitative algebra point of view, this is as nice. These are as nice as it gets. So let's do to understand if we can look at the complex. At the we can check, well, it's clear, it's a ball, so it's clearly contractible. But if we look at any induced subcomplex, we're going to get something contractible or analogously acidic over any. Those two things turn out to be equivalent. And linear resolution, so look at elements, generators of the standardized ring. There's some relations between them. So for example, x2 and x4 and x2 and x6. X2 and x6 are generators of the standardized ring, but there's some relations among them, so called Cs. And if you write relations to cancel them, you only need to put linear terms in order to do so. So, you want resolution over the polynomial ring. Every time you encounter relation between the CCGs, this relation is linear. So linear terms of the polynomial ring or cancel at each step.
So, question about this. Probably induced subcomplexes are contractible.
Mm-hmm.
So in this example, if I look at the subcomplex induced on vertex 2, 4, and 6, I just disconnected vertices 2, 4, and 6. Am I interpreting that right? Is the statement that every component is contractible, or?
Ooh. Yeah, probably something like that. Oops. Yeah. Yeah, if it's contractible.
Okay.
Yes.
That makes sense. Thanks.
Yes. Because, yeah, this is only going to start telling you stuff about one skeleton. So yes.
Great. Thanks.
Yes, you have vertices which are disconnected, and that's, yeah. Okay, so all these graphs are very nice. We can ask the following. Can we say that instead of having a graph, we have a high-dimensional simplicial complex? And what is the skeletons of these simplicial complexes? And ask stuff like, is chordality for such complexes? So try to understand. Can we produce analogs of for K of a simplicial complex, or for K minus or for cases of simplicial complexes? Logically, can we do it combinatorially? For example, from before, the one in terms of topology and algebra still holds. Can about cuts, can work about elimination of vertices and faces. So is there a nice recursive structure, or some classes with a nice class of simplicial complexes that does similar things? And what to argue is that the right way to think about these questions, which I addressed in the literature several times from a pure combinatorial point of view, it's the answer, or what to advocate is that we should be actually thinking about the topology of the complex in order to answer this question. So let's look at K. Let's talk about simplicial. So I'm going to talk about simplicial homology, and so let's talk for integer K. Let's fix a K cycle sigma, and the sort of this set of vertices in one the faces of sigma that has non-zero coefficient. Okay. So if you look at just the simplex alternating sum, would be the vertices of such a simplex. And to define a simplicial complex to be chordal over K, because in order to talk about K cycles, I need to have a field for phase ring for this. I'm going to chordal if so K cycle is the if K plus one cycle that does not need more vertices in order to the boundary of a K plus one cycle with no more vertices in the support. Okay, to four, we can say, well, look at the cycle 1, 5, 3, 2. That cycle, and the sum of the 1, 5, 3, 1, 2, 3. Okay, and the complex which is a boundary, whose is this cycle, is find a relation of the polygon in some sense with new vertices. So if I had a square with a point in the middle and a pyramid over it, that would be chordal, because I point in the middle in order to resolve the cycle. Oh my gosh. An equivalence is, well, we can say that a complex delta is k-chordal if and only if the homology of a complex, the reduced homology of every induced subcomplex over k, is zero. So this condition that I don't need to introduce any new vertices to find a cycle, not as my boundary, I don't vertices. That means that I live in an induced subcomplex. So every induced subcomplex has Banach-Shade homology.
So, definition, this is for k-chordal?
Okay, yeah. It's chordal, yes. The definition above is k-chordal, which is, so in the equivalent part I have k-chordal. Yeah, so positive integer, greater than 1. It can be 0, actually. It can be, let's actually means for it to be 0. Zero chordal means that the reduced homology of vanished subcomplex, and if any two vertices of this graph, the induced subcomplex is either the 2 points or the edge between the 2 points. It's only going to be, so the zero reduced homology is only going to be 0 if present, and means that a complex is zero chordal if its one skeleton is a complete graph. Okay? For a graph G is going to be one chordal, so the relationship between graphs and this notion of chordality is a graph is chordal only if its clique complex is one chordal. Okay? And we skip the remark, which I'm going to make it later to talk to address durability. But let's notice another nice thing that happens graphs, which is that you have a graph by acidity in high. If I have a graph which is when the clique complex of G is k-chordal for every k greater than or equal to 1. Okay. My reduced homology induced subcomplex of the clique complex of a graph. So remember the theory here. All subcomplexes are have growth reduced k over G. We get this phenomenon that one quality implies chordality for every k, and we can think so k, the phases and the k plus 1 phases. So I'm originally a combinatorialist, and I would say this is so 1k, but this is a combinatorial property of the k and k plus 1 phases of the simplicial complex. So it helps to fill all possible k plus 1 phases and constrain. So if we fix the skeleton and add as many k plus 1 phases as I can support without altering k skeleton, we say that this is a property of the k phases. That's combinatorial. Yeah.
I'm trying to understand this, and I think I'm a little confused. So, if we take, for example, the affair, so that's not chordal,
no.
And chordal, is that right?
Because it's not complete, right? So
The diagonal isn't there. But one chordal.
So you, in order for the square, so you diagonals, right?
So one chordal?
Huh?
Mission again. So where's this one chordal?
It has first homology.
Oh, okay. You have to look at, okay, because there's a one cycle and that's the boundary. Okay.
So all the subcomplexes, including the simplicial complex that you're starting with, so you can think of the induced subcomplexes taking all the vertices. All of the induced subcomplexes have to have vanishing homology. Look, I'm highlighting it here. So for induced subcomplex, the case homology is equal to 0. So put first homology equal to 0. The square is not because it has first homology. So the clique complex of the square here. So clique complex is one chordal. It has a 4 cycle with no chord.
Okay, thank you.
But this is so having all these homologies, all these bunch.
So I ask one more question, if you don't mind me interrupting one more time. Your condition here you've given as the selection of local conditions. Does that differ from saying that the reduced K homology of the simple complex delta is 0?
So it implies that the reduced K homology is 0, but it's much more, right? So for example, let me show you an example here. Do you see that complex over there? So it's diagonal and two field triangles.
Yes.
Right? So the content of the theorem is, well, look at, so this is going to be one chordal.
Mm-hmm.
This one is, well, look at the one homology. So the first, this thing is 0. If I look at any subset of the vertices and I look at the induced subcomplex, it also has one vertice that disappears. Okay. Interest. Let me draw another example, which is a non-example of chordality. It's at the same 4 square, but I put a point in the middle, and I draw all the 4 triangles going to that from the edges. That first homology, which is reduced, but it's not chordal, because take the induced subcomplex on the boundary of the square, you get a square which has which non-trivial homology. You get a circle.
Yes.
That's thank you for the question.
Fits with your original definition, because the boundary of the square can be filled in, but it can't be filled in without adding more vertices, in particular the vertex in the middle.
So we think of exactly, if you think of the homology, so the one cycle of there. So it's one cycle, but if you want to resolve it, if you want to write as a boundary of something, you really need to add this extra point in order to kill it with homology. In homology, you do not complex. Okay. Good. So I introduced the linear resolution business, and so for a long time the commutative algebra community has been concerned with this property of real notions that lead to linear resolutions, and here is one reason why the thing happens, with term of Egon and Reiner. For the you know a little bit more of Stein-Reisner theory, but we got a simplicial complex delta has a linear resolution leave the Alexander dual of delta, which is another simplicial complex combinatorially defined out of delta, is Macaulay. So Macaulay means that the ring, the Stanley-Reisner ring of Macaulay ring, and so being Macaulay means that the link of every phase only has reduced homology. For reduced dimension in the dimension of X. Even so it's a classical theorem of Hochster in this transition between commutative algebra and topology. So in some sense, we know. So we kind of know this is the linear resolution business. We know that in one dimension, in one graph, this is sent to graph by passing to the complex. So maybe to try to find that this is a good notion of chordality is to go and so you know this resolution business since coniness and homology is understood as homology and this Alexander duality. So we could expect to topology trying this notion and trying to figure out what's the right notion for chordality. If I have something with a illusion, don't know the text of this chordality. Do these complexes satisfy? So yeah, with something with a linear resolution, I get some homological data from combinatorial topology, and then I can ask what kind of chordality, which is another property, do I satisfy whenever I have this resolution, or can I come up with a right notion for this just directly with the complex without worrying about duality and Reisner or anything like that? So let's talk a little bit about what this means. Of the graph, one applies all kinds of chordality. Contractibility property. The way chordality so far, so chordality does not imply K plus 1 chordality. The first obstruction is a pretty trivial. Look at the boundary of a K plus 1 simplex. In homology, it's K. So of a K complex, it's K chordal, but not K plus. Yeah. Here's. I lost. Okay. So, yeah, simplex. It is. It has zero. If you remove, if you take n Deuce subcomplex, actually get something which is a cone. That means change this one for a 2. One chordal because it's a K plus 1 sphere, and it's so all the other induced complexes, all the proper induced subcomplexes are going to work, but it has no homology, so it does go up, even though but this has an issue, which is that so the reason why this has homology is because the reason why K plus chordality fails here is because we have all, maybe we can assume that all the minimal non-phases of our simplicial complexes have K or S, which is what we're doing with the chord graph, click complex of a graph. So if we take the graph and we take the click complex, all the minimal non-phases are edges, So maybe if we start with a complex, we can face dimensions less than k and ask the question for that complex instead. Ask whether it has some property like that. But the point is, even if I feel all I can feel, and that all my missing faces are in the k or less, I can do problems. So for instance, the simplest thing that we can do, take the join of the k simplex with itself, the simplex with itself. So simplex with two k, two vertices, missing faces, two minimum faces, which are two disjoint dimensional faces, plus one. This simplex, so this is the join of two spheres, and therefore here, so it has non-trivial 2k plus 1 homology, 2k minus 1 homology. A simple exercise to check that k chordal, k plus 1 chordal up to 2k minus 2 chordal. In some level of chordality does not imply the next one, which means that some sort of bad issues. However, some good news, those are obstructions. So this theorem here is what happens with chordal graphs. And generalization for this phenomenon that in the clique complex of a chordal graph, so in the clique complex of a graph, one chordality implies all the other kinds of chordality. Oh, where am I? Sorry. Yeah. So the example, which was k plus 1 up to 2k minus 2 chordal, but no k minus 1 chordal, with dimension k, is, so we can say a complex with no missing faces of bigger than k, so we fill all high dimensional holes, are equivalent. Delta is chordal for L 2k minus 1, so it's of chordality forever.
And it was the graph case, because if you plug in k equals 1, you get if it's one chordal, then it's chordal forevermore. That's nice.
So the analog of the graph case, so it's out. It does not go up for a good reason, because when you take joints, you can take higher dimensional holes. But if you take joints of things that have small dimensional holes, and you guarantee that there's a space in the complex where you did not introduce holes, that means you don't introduce holes up to dimension 2k minus 1, don't introduce holes at all. Okay, so a nice that people in commutative algebra care about, we can say that the standing of a simplicial complex has linear resolution, which is the analog of this theorem by Froberg, if all missing faces are of dimension k. So I have complete k skeleton, k minus 1 skeleton. The missing faces, or the Stanley-Reisner ideal, is generated in degree k. My matrix is k is L chordal for all L in the range to 2k1. And so from the algebraic point of view, and from the classical Stanley-Reisner theory point of view of simplicial complexes, this is the right notion of chordality. Or it seems, right? Now, people, so let me make remarks about these theorems. First is time, right? As a join of the two simplices show, the join of two k simplices show, you can go, so you really need to check chordality in dimensions k plus up to 2k minus 1. That's the thing, because even if you go up only up to 2k minus 2, you get examples where this thing fails. And So computations, this is an economical, so you can rhythmically check whether a simplicial complex is Cuddle. You can pass to the Alexander dual, but that's a computation. Here. So it's still very costly because we have to look at all the subsets and check whether homology vanishes between in the ranges k and 2k minus 1. But this is a much smaller test. It's an a more economical version of doing this. So I would guess that this is computationally very hard, but it's a more direct way to check whether you have these nice properties. Issue that we run into is that chordality is field dependent, right? Unlike the graph case, in which we could pick our favorite field and everything would work to the field, there are examples of simplicial complexes which are Cohen-Macaulay over, but not others. And here, so by this we get complexes which are chordal some fields but not others, which kind of about being chordal over every field. There's a solution. Just think about the homology groups of integers, right? So if integer homology vanishes, you can say it vanishes for all the fields. And the universal coefficient theorem, that's actually equivalent. So that's an equivalence. So it seems like if to be picky and a specific. So if you want to make sure that it works for any choice of fields, you can pass homology over the integers. Which with me that this is not combinatorial, but I still think that if you're in simplicial complexes and you're talking about simplicial homology, this is somewhat a combinatorial. So it's like combinatorics and topology. So examples in conclusion, and from the things I've told you about, they're kind of tricky to come by. So I told you this grew up from so we were studying polytopes originally. A very nice class of polytopes is that we're going to say that a translation of a ball, of a d-dimensional ball, is stacked if the skeleton of is in the boundary. So in the of my ball, I have high dimensional faces. Okay, and it turns out that in polytope theory, examples of complex k-stacked balls. So then phase numbers of polytopes, this stacked ball, k-stacked convex k-stacked balls play a significant role. So it took me a long time to come up with, so to draw an example that is not graphs, but it is k-stacked chordal K's are called for greater than or equal to k. Studies this homology able to come up with quantitative lower bounds for polytopes, so we can show theorems about metric geometry, polytopes, and counting by studying chordality properties. But so let me instead of going into this, which is a completely different field, let me talk about the property. So the properties about perfect elimination, and I'm going to talk about causes. I'm running out of time, but the point is we can still talk about stuff like the RAM, about shedding faces or complexes. So removing once at a time and having inductive definitions. But we can talk about Dirac theorems in terms of chordality. chordality. So is that a one chordal complex? So remember that chordal complex means that so in a one chordal complex, the of the complex is a chordal graph. Dirac theorem tells us that there's a vertex or neighbors induce a complete graph. We can actually say that in Dirac theorem, statements of homological chordality says in a chordal graph there is X whose link to a chordal. And also, Dirac that if we take one chordal complex and we so a minimal subset of vertices that separates two vertices, that is core subcomplex, which is a complete graph. I want to ask what the analog of Dirac's complexes in well, if I have a K complex, can I have a face or a low dimensional face? I'm going to make this more precise a little bit later. So, or the ended link, or the appropriate notion of link, is just one chordal. So can I use K chordal implying K minus one chordal for smaller things, and then I'm gluing my simplicial complex by induction in terms of chordality. Or I find an appropriate notion of K minus one cycles, can I of K of cuts of the skeleton, so I get two subcomplexes which are K minus one chordal. So for definitions, let me talk about. So I have of a complex. I'm going to talk about the extended link, and the link is all link, except it's just the set of faces of that I do not sigma to be a subset of delta. I join us in the usual link. That T union delta is a point of my complex. So you think of this as the usual link of sigma. Complex of K links, which is a notion that I mentioned earlier. If I start with a simplex, I'm going to add. So a skeleton adds every missing of dimension higher. The theorem. Let me just say that this notion of chordality as it is field dependent, and we want combinatory. So we want a combinatorial notion. It's field, so you can expect that there's going to be weird things happening. And for example, Duns. So if you look at the Duns cap, which is this with orientation of the very glued together. You can search it Wikipedia or any contractible space which is not collapsible. You can take so you take the Duns cap, take the barycentric subdivision or triangulation. That so the Duns cap is a contractible space. Every edge belongs to exactly two triangles. In the couple, so it has second homology that vanishes, and that actually means that there are no twos because it's two-dimensional. So it's really two chordal. Think of everything. So just for you to sit down and every edge belongs exactly to two faces means that every link of either a vertex or an edge is at least 4, which is a cycle of length at least 4. So you have which is trivially two chordal, but not 1/4. A link. How can a complex to be K-Dirac? So I'm going to say that my spatial complex K Dirac if is equal to the K skeleton of some simplex dimension at least K. The K simplex, so the K skeleton of a high dimensional simplex is K Chordal. That is a simplicial complex that we understand pretty well. Phase of dimension at most K plus 1, such that when I remove this phase, I look at the subcomplex not containing sigma, which is K Dirac, and the of sigma is K minus 1 Dirac, a combinatorial condition on how these things glue together. Let's not do what it means, but it means that, so fill the K minus 1 dimensional holes in the extended link has something to do with filling the dimensional holes in delta first and then passing to the extended link. Point is, this you define recursively, and dimensional K, they actually coincide. So it's 1 Dirac if and only if its graph is a chordal graph. So it's equivalent. So in dimension 1, these two notions are equivalent. And 1 Dirac is this 1 chordal, but yeah. So but K implies that filling the holes gives me chordal complexes. But converse is not true, right? Because this is a pure combinatorial definition. It works for every field that you choose, but not. So we're mentioning that can also be defined and so what's also be defined? Constraint properties. You can find this in the paper. Notions that are wide open. So we don't notions, and they're better definitions. So I would be happy to see a better one. That's pretty much everything I had to say. Thank you very much. I'd be happy to reply now or by email or Skype or via here whenever. This is a nice tool that's in computation.
I have one question. You alluded, is it correct to say that there previously, before your topological definitions, there had existed some algebraic definitions of higher generalizations of chordality? Is that right?
No, combinatorial ones.
Oh, chordal ones.
There were chordal ones in terms of the missing phases, but most of them were in some of combinatorial. So, simply K Dirac thing, like if you look at the minimal non-phases and it has this combinatorial structure, then we have a linear resolution for every field.
But its topological definition gives
general Yes. So this is like a recursive. This we believe is like the best analog of Dirac's theorem. Might be something better. So we cannot prove that. We cannot in some sense, because it's slightly subtle, but I think it's kind of interesting. There's something nice.
No, this is not related to your motivations, but I'm just if you have any thoughts on it. So, you give a definition of higher chordality as in goals, say K cycles could be filled without adding any more vertices. Right. This is a topological definition, and it was also homological. You couldn't try to give a topological definition of something different, where it's more homotopical. So things like spheres can be filled without adding any more vertices. So this would probably not map as well with the algebra that's going on, but might this be interesting at all, or might this relate to your homological definition?
So with it. So my issue is that I'm not a topologist. I'm not an expert in homotopy. There's for example a notion of homotopy Cohen-Macaulay or Cohen-Macaulay complexes, which you could probably translate into homotopy. Homotopy chordality, right? So if you do it homotopy and have all the homotopy groups vanishing, then you probably a lot of things of the homology would be probably a more class. Sometimes working with homotopy groups in combinatorics, so I don't really know how to do it. But I know that in certain instances you can do stuff. So you find something to be homotopically chordal, and about the binary induced subcomplex and see what happens.
Right.
It's less clear. So and then all these things of plating and chordality. So chordality in a certain range being 0, implying higher chordality going away and be much tougher, right?
Right. For Jose?
I was thinking along the same lines as you, Henry, there.
Yeah.
So that was good to have that discussion. Thanks. I enjoyed having that discussion. So.
Okay. Let's thank Jose again. And recording. So Jose, I'll post